Hi, my name is Manish Gupta, and in this video, I'm going to talk about video-to-video translation, video object tracking, and video super resolution using the CoDeF model. Right? So aren't these tasks interesting? Right? They of course are. So let's get started. All of these tasks basically involve video generation. So therefore, let's get started by asking this question: why is video generation challenging? There's several challenges in video generation. One, maintaining high temporal consistency is a task which is complicated by the inherent randomness of neural networks. So, if you compare it with the image generation task, you don't really have to care about this temporal inconsistency part at all, right? So you basically just generate one snapshot and you're done, right? But then if you generate one image and you want to generate the next frame in the video, that's very complicated because on one hand, there is randomness in these neural networks, and on the other hand, you have to maintain temporal consistency when you're generating frames in a video. Second, videos also include textures of inferior quality compared to their image counterparts. So if you look at images, typically, if you are just looking at image generation data sets, they have very sharp things in general, right? While typically videos will have textures which are of slightly inferior quality. Videos necessitate greater computational resources, clearly, therefore any video analytics is difficult. And then ensuring subtle motion details such as blinking eyes or slight smiles, etc. in the reconstruction is difficult, right? So essentially, in general, broadly generating seemingly okay videos is easy. But then if you want to really go into deep details, very small little details about blinking eyes or slight smiles, that's complicated to do when generating videos, right? Now, then the question is that, well, the image generation world has progressed so much, video generation has not progressed much. So is there a way of making use of this progress in the image generation world into the video generation world? Right? Is there a way of getting that kind of transfer of information or transfer of methods and technologies? Right? So, or in other words, the question is that is it feasible to represent video in the form of an image to seamlessly apply whatever are the established image algorithms to video content with high temporal consistency, right? So can we transfer or lift the algorithms from the image generation world to video generation world? Okay. So that is the question which is answered in this particular paper and in this model called as CoDeF. So CoDeF stands for content deformation field, and it is a new type of video representation model such that these video representations lead to very accurate video generation and therefore support several downstream tasks like video to video translation, video object tracking, or other such tasks, right? So the way CoDeF works is that it basically uses these two different kinds of hash tables in some ways. So a 2D hash based canonical content field and a 3D hash based temporal deformation field. I'll talk about these in detail in the remaining part of the video, but the idea is that CoDeF primarily uses these two hash based fields. So one of them is called as canonical content field. In some ways, you could basically say that, hey, if I have a video clip, what is the central, and if I were to represent it using a single image, then what is that image going to look like? Okay, so that is basically what is called as canonical content field or canonical image for that video. Okay. Uh, so that's that, and it basically uses 2D hashes so as to essentially accurately get that particular image. So the 2D hash is sort of required to map every XY position to a particular color, RGB color value, right? So in the canonical image that is representative of the entire video. Okay. So the broad idea is that for the entire video that you want to generate, you first generate the image, and then from that image, you want to sort of do slight temporal changes to it so as to actually make it really like a video. Okay, and those temporal changes are done using this 3D hash-based temporal deformation field. Okay, so you want to temporally deform this canonical image such that basically there is consistency across those frames, and then yes, there is some motion which is happening, which leads to the video generation. Okay. So this 3D hash-based temporal deformation field records the transformations from the canonical image to each of those individual frames that will be in the video. Okay. Now, the idea is that given a target video, these two fields are jointly optimized to reconstruct it. Now, of course, in this video generation model, the idea is that given a large video data set, you want to effectively train a model so as to first learn the video representation and then essentially try to reconstruct the video. And while reconstructing, of course, the model learns how to generate new videos, right? Or how to basically do these video generation tasks conditioned on an existing video and so on. Okay, so that's that. Now, also while generating, right, while generating videos, what they found is easier to do is to generate the coarse frames for every, coarse level frames in the video first, and then get into fine-grained details. So this coarse to fine training helps achieve a balance between the naturalness of the canonical image and the faithfulness of the reconstruction. Okay, so remember there are 2 or 3 interesting things that you want to optimize. One, you want to ensure that if you have a video in the training set, you want to come up with representations such that you can reconstruct the original video back. Now, reconstruction basically involves 2 things. First, you must be able to get a very good canonical image from that video. And second, you must be able to capture those deformations that are required in your 3D hash-based temporal deformation fields appropriately, right? So therefore, what you need is this, your 2D canonical image should be as natural as possible, and your 3D temporal deformations should be as faithful as possible so as to give you very good reconstruction. And they do that particular thing in a coarse to fine manner, where you first try to generate very coarse image frames in the video, and then you basically try to get the fine-grained details. Okay. So let's get a little bit into detail about how this works. So what are these content deformation fields? Well, there are 2 content deformation fields, the 2D content canonical field C and the 3D temporal deformation field D. Okay. So, and as you sort of understood, this works in a multi-resolution manner. So there are coarse fields, and then there is a more fine-grained version. Okay. They're basically supported by these 2 components, a hash table and an MLP. So there's a hash table associated with the canonical field, and there's a MLP associated with the canonical field. There's a hash table associated with the deformation field, and and also an MLP associated with the deformation field. Okay. Now let me actually get a little more concrete what these things are, right? So the idea is that the 2D content canonical field, it's basically, yeah, of course, it's related. It works at multi-resolution level. But then what it is supposed to do is to take any XY position and map it basically to a color value, right? So to a color value. Now, so the idea is that you take any XY position and you must map it to a color value, which is basically which is basically there in the original image. Or what you also want to do is to basically also map it to, let's say, F features at L different levels. Remember, we basically want to create this 2D hash kind of functionality, such that it basically gives you a representation of the canonical image at different resolutions. So if you want to get at different resolutions, you want, of course, a particular function to map the 2D position xy, or you can call it x as the overall xy position, to a color value. But then you also want these to be finely interpolated so as to basically get these mappings at different levels of resolution. Okay. So that's that. So essentially, yes, you will use some hash functions so as to essentially first get a transformed representation and then apply MLP so as to essentially get the color value associated with every XY. Yeah. And then what you want to do is to essentially use linear interpolation so as to get these values at different levels of resolution. Okay, so that's that. Now, so in those ways, basically the 2D content canonical field maps every XY position to 2 plus F into L different dimensional field, where 2 basically just represents the overall the original image itself, and F into L basically represents at L different levels F different features associated with every pixel, right? So that's that. Now in the 3D temporal transformation field, temporal deformation field, now why do you need this? Because you want to actually take a video which contains several frames, right? So let the video contain T different frames, capital T different frames, in which case, you can represent any point in the video as XY in that frame, but then that's the Tth frame. Therefore, you can represent any point in the entire video as a XYT, 3 tuple in that senses, right? Now, what you want to do first is to be able to take any such arbitrary position in the Tth frame and then encode it using some sort of a hash encoding so as to get a high dimensional feature representation, and then apply an MLP so as to actually map it to a position in the canonical field. So you have a canonical image, that's great, but if you take any frame, you must be able to first come up with some sort of a high dimensional representation, and then finally say that, hey, I must have an MLP which can actually help me connect it to a canonical image. So you basically use an MLP to map your multi-resolution based deformation field, a 3D hash based deformation field, into 2D coordinates, which can then map to the canonical image. Okay, so that's that. So therefore, you see, I mean, the hash functions, of course, do not require any learning, but what requires learning here is the MLPs. So, and these MLPs, this is one ML, the first MLP, the second MLP. These MLPs are the ones which basically learn how do you map any point in the entire video to a canonical field in that senses. Okay. So that is that. I mean, the idea actually is pretty simple. All you want to do is to basically have like a canonical or a representative image. So for example, in this video, I'll show the video later as well. This is the canonical image. This is the canonical representation of the image. And then what you want to do is to ensure that each of those frames can be sort of every pixel can be actually mapped to a particular point in this canonical image using 2D hashes or 3D hashes, followed by MLPs. Okay. Now, of course, when you do this, since you're doing multi-resolution, therefore, in general, for the highest level of resolution, you actually use these hashes and the MLP. But then for lower levels of resolution, you try to do interpolation so as to essentially get to the different levels of resolution that you have, right? Now, while doing this, of course, in the 2D case, you essentially do linear interpolation to get higher granularity representations. But for 3D, you basically want to do trilinear interpolation because you have 8 neighboring points for every pixel. So as you see here, the interpolation basically makes use of 8 different corner points. Now, how is this thing trained, right? Of course, how is the CoDeF model trained? So you basically use a whole bunch of videos and then you try to train this model. The first loss, of course, that comes to mind is reconstruction loss, right? So you want to, of course, make sure that when you have a video, you basically do a 2D hashes, 3D hashes, learn MLP, learn a good video representation in terms of these 2D and 3D hashes and then the MLP. But then when you try to reconstruct the image, reconstruct the video, it should be as close to the original as possible, right? So that's a reconstruction loss. And then you have a flow guided consistency loss. Now that's very interesting. So what is this guy, right? So this guy basically says that you have these representations, the canonical image representation at different levels, right? So if I consider any particular level, right, the corresponding points which are identified by the flows with high confidence should be the same points in the canonical field. Okay, so the idea is that, of course, in a video you have several points across different frames. Now, if basically I use flow vectors, I can actually figure out which are those corresponding points, right? So you can actually use these image processing algorithms to compute in optical flow vectors. So essentially, if I take a particular image and I take a flow vector, and I warp an image using that flow vector, I sort of get the image or the frame at it+1, right? So that's basically what I get. Now, if I basically apply the reverse flow vector, right? And I warp it again, I basically should get back it again, right? Or rather the original image at the time point t. Well, here it is I rather than t. Sorry, yeah, I rather than t. Now, the idea is that if I basically look at these flow vectors and they're able to capture these flows nicely, this warping in the reverse direction should give me as close to II as possible. Okay. So what is this guy capturing? This guy is basically capturing how confident I am about my flow vectors, right? How confident I am about those flows, how confident I am that there is good transition between these points and not sudden short changes. Okay. So for such particular transitions where there is a very smooth transition, very high confidence, optical flow which is happening, I want to minimize this loss. And what is this loss? This loss basically says that, hey, if I basically look at the frame at time point t, and I look at the frame at time point t+1, and I'm basically using this deformation field so as to map the points in these deformation fields to the canonical field, then what I want to expect, or what I expect, is that these high confidence so the corresponding points, because of this high confidence with high confidence flows, should map to the same points in the canonical field, right? If they do not map to the same point in the canonical field, well, we will penalize it because you're taking this norm, right? So basically you're taking the differences. Okay, so that's that. So that is basically called as the flow guided consistency loss. It's a very simple conceptual definition that, hey, if I'm very confident of the way the flow is happening across different frames in a video, then for those points across those frames, they must map to the same canonical canonical point to the same point in the canonical image. Okay, so that's that. Now, there's also this another loss that they define called as grouped content deformation fields. Okay, so this is not really a loss, but then this is another way of making sure that the training happens really nicely. Okay, so what happens is that typically in any image or in any video, there could be several objects which could be flowing in their own ways, right? So imagine like a cat running behind a dog. Now the cat may be running at its own pace, the dog may be running at its own pace. So the idea is that their flow fields are very different. Therefore, what you don't want to do is to or what you want to do is to track them separately, right? And that is why it could be a good idea to have, so these are called as complex motions, right? Complex motions arise from overlapping multi-objects, and they may lead to conflicts with one another, with one canonical, right? So if what you want is maybe you want a canonical image for the cat, a canonical image for the dog, okay? And what you could do is to basically use this thing called as segment anything track, so as to get segmentation of each video frame into case different semantic layers along with their mask. So what this segmentation guy does is that it's not a segmentation over an image. Well, it's a segmentation over the video. So it's basically like doing video object tracking in that sense. And once you basically have done that, you basically have k different semantic layers in some ways, or k different videos, if you will, right? So for each layer, you can basically use a group of canonical fields and deformation fields. So rather than having one canonical field and one deformation field, you basically have k different canonical fields and k different deformation fields if they were like k objects that you are trying to track. Okay, and this k is basically defined by a segment anything track. I mean, this particular segmentation algorithm, which tells you how many segments are present in this video. Okay, now. So basically that's called grouped content deformation fields, where you basically try to learn canonical field and the deformation field separately for each of those k different segments. Okay. So, and there is some complexity which I'll sort of skip here, or rather mildly talk about it. So the idea is that now if you have these masks, so if you basically have the cat and the dog nicely, that's great, because you can basically try to optimize for the good canonical image for the cat and capturing the flow appropriately using the deformation field for the cat, right? And same thing you can do for the dog. But how about the background, right? If you basically just focus on the mask for the cat and the dog, the background gets missed. And therefore, what you also end up doing is to add some pixels. So when you're trying to optimize for the cat, you basically also add some pixels from the non-masked region, non-cat region, so that basically you ensure that random and unstructured patterns don't appear in the background region. Okay, so that is basically handling the background pixels also. Okay. So overall loss function looks like this. You basically, of course, try to optimize for the reconstruction loss. You also want to optimize for this flow guided consistency loss. And lastly, if you care about the grouped content deformation fields, you basically have, one mask, one canonical field and deformation field per mask or per segment. And then you also need to care about the background loss, loss for the background pixels. So that's that. That's how it works. Now, here's the fun part, right? Let's see where all people can have applied CoDeF, right? So CoDeF basically, of course, takes time to do these kinds of things. So it basically takes about 300 seconds to estimate these fields. Okay, but that's not very, that's not too much of a time, especially when you think about other softwares in this kind of work, right? In their paper, you can read about more details in the paper with respect to baseline, but they basically saw that the kind of quality that you get after, when you do video processing applications is actually much better compared to the best baseline. It's 4.4 increase in PSNR compared to the best baseline, right? So here is an application of CoDeF. You have learned how to do video processing, using these 2D and 3D hashes, the content canonical images, and and the 3D deformation fields. Now, one of the application is video to video translation using control net. So the idea is ControlNet is a popular architecture for basically doing image-to-image translation. Now, what you could also do is to take it to video world, because after you essentially represent the video using the canonical image and deformations, you could basically just take the canonical image, apply the ControlNet based translations in the image world, and then try to convert them to the video world using the deformation fields. Okay. So as you see, it basically does super high quality job. So here you essentially see this kind of a video getting converted to another kind of a video. And again, these conversions basically happen because of ControlNet, where you actually give text-based instructions as to convert one kind of image to the other kind of images. This is like a cartoon kind of kind of conversion. This is yet another comics kind of conversion, and so on. Okay. Now, you could also do object tracking. So essentially using segment anything. So in fact, here, as you see in this particular thing, in this particular video, so this is the input video, and what is being tracked is his eyes. So if you really look at it, these eyes are basically tracked across frames. And thanks to the deformation field, which maps to the canonical field, you can actually map the eyes across frames to the same canonical points, or the points in the canonical field, and therefore track these segments appropriately. Right. So segment anything can be run on each of those frames, so as to basically get the eye segment, the blue colored thing that you see here, and then those points can be mapped to the same canonical field, so as to say that yes, this is the same segment which is being tracked across different frames. Okay. So the nice part is that this is so powerful that it can actually also track non-rigid objects like water and smog. So typically, object like phone or laptop, or or many of these things are pretty rigid in nature. Of course, humans are non-rigid because across frames we move and so on, but we are still fairly rigid, right? So, but if you think about water and smog, they basically move in a very, very non-rigid manner. Tracking them is actually very complex, but they basically show that yes, it's possible to track very accurately these kinds of non-rigid objects as well. Now, of course, you can also do video key point tracking. So essentially, you can basically say that across frames, this eye and this eye, you can actually track nicely across different frames and accurately predict those things. Right? Now, there are other kinds of applications that are possible, like video super resolution. And remember, all of these are possible because every frame in the video can actually be mapped to a canonical image, right? And if you can do super resolution for the canonical image, you can basically use just that canonical super resolved image so as to use the same deformation fields and have the super resolved video. Right? Similarly, you can also do user interactive video editing, where if you have a video with different frames, the user actually just makes a very simple change in just one of those frames, and then you can actually propagate this change from one image, one user edited image, to all other images, because you can just treat that change as the change in the canonical image, and then that can be propagated using the deformation fields to other images. So in summary, in this video, I talked about the CoDeF model, which is the content deformation field model. It's a new type of video representation, which consists of two parts, a 2D hash-based canonical content field and a 3D hash-based temporal deformation field. The 2D hash-based content canonical field sort of leads to a canonical image representation of the entire video, while the 3D temporal deformation field records the transformations from the canonical image to each of those individual frames, right? And then we also saw how CoDeF model can be used for doing various kinds of downstream video processing tasks like video to video translation, video object tracking, video super resolution, and user interactive video editing. Okay, so that's it. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.